Good morning, everyone. Today, my name is Liu Yang from the Hong Kong University of Science and Technology. And today, I'm very glad to be here to show my work about the metal 3D printing. And so here is the outline, including 5 parts: the introduction, problem statement, methodology, experiment and discussion, and then the conclusion. And first, let me give an introduction of this study. So in recent years, metal 3D printing, also called metal additive manufacturing, is developing rapidly in many areas, including the construction industry. And there are a lot of benefits. For example, the complex shape production, cost saving, fast transition, and carbon reduction. And there already exist many examples of the metal 3D printing in construction, from large-scale structure, like the metal bridge, to small components, like the innovative joints, like the lighting node, the facade node, with topology-optimized design, which can reduce weight and stress, as well as structural components with customized design, like the rebar with varying thickness and hollow sections with some adding features. And metal 3D printing can also be used to repair existing structures on site. And due to this, we can see that adopting metal 3D printing in construction allows greater flexibility in customized design, innovative design, and authentic features. So let's go deep to see what is the metal, what are the major technologies of the metal 3D printing. There are 2 major groups. First is powder bed fusion. And it works like this: a spread of powder, a layer of powder spread on the bed and fused by a laser. And when one layer is finished, the bed will lower down and another layer will be formed. And in this way, the printed size is limited by the chamber, and only single materials can be used. But it has very high accuracy, so it most often used to build new parts, which requires high accuracy. And another major group are direct energy deposition, where a nozzle is carrying metal materials and laser together. And the deposited object will be formed when the nozzle moves along the design toolpath, like this. And in this way, the printed size will not be limited, and there multiple materials can be used together. And it is effective for repairing existing structures. So comparing these two, we can see that the direct energy deposition is more suitable for the construction industry. So my research is mainly focusing on this technique. And to adopt this advanced technique in construction industry, geometry inconsistency is one of the main concerns. During the printing process, the track geometry is determined by the controllable process parameter, also called printing parameter, like the feed rate, laser power, or printing speed. And it's also determined by the uncontrollable process parameters, like the nozzle to the top surface distance, the previous layer height, and inner layer temperature. And because there are uncontrollable process parameters, the track geometry often deviates from the design value, even when constant printing parameters are used. So geometry quality assurance during the printing process are needed. When we give the fixed process input, the fixed printing parameters, the geometry might deviate. So we can then we develop the process monitoring system to monitor the uncontrollable process parameter as well as the geometry attributes. And by qualifying the geometry discrepancy, to compensate the geometry discrepancy, we need the geometry control. And to achieve geometry control, we need to understand the relationship between the process parameter and geometry attributes. So the geometry estimation, which is to identify the relationship between the process parameter and geometry attributes, is a very important task in metal additive manufacturing. And existing literatures for the geometry estimation use empirical model, which only consider printing parameter or for single layer, single track. And the physics-based model with numerical simulation will give us better understanding of the complex laser material interaction process, but it has low accuracy. And in addition, the geometry problem often occur at corners due to the acceleration and deceleration when the nozzle moves at the corner part. So in my study, I want to estimate the layer height of multi-layer corner deposition using machine learning methods. And here are the overview of the proposed method. First, so it includes 3 parts. First, I use a large amount of straight line data to build a initial model for the geometry estimation of straight line. And then because the experiment is very expensive, so we want to use small number of corner data to obtain a model for corner deposition using transfer learning method. And then to better improve the performance, we want to do the online updating of the geometry estimation model. So here are the details. First, we select the initial layer height estimation model using a large amount of multi-layer straight line data. We select 6 machine learning algorithms and consider printing parameters and process parameters. And we have 15 feature combinations for each machine learning algorithm and feature combination. We train and test and then select the best algorithm and feature combination. And finally, it turns out to be the AM model. And then with this model, we have a large amount of multi-layer straight line data, and we want to save effort in collecting a lot of corner data. So we newly collect a small number of multi-layer corner data, which only has the process parameter, and use transfer learning method to obtain a geometry estimation model for corner estimation. And to develop this geometry estimation model for corner deposition, there are a lot of transfer learning techniques. And in our study, the problem can be identified to be a domain adaptation problem, since the feature space and the category space are the same, but the data distribution are different. So so this is a data adaptation problem. Given the labeled source domain data and unlabeled target domain data, we want to find a classifier that can used on the target domain data. And the main part is to calculate to find the distance and minimize the distance between the source domain data and target domain data. And we use the maximum mean discrepancy and train the model on the new feature space. And this is established domain adaptive neural network model. We use AM model from the straight line data and add the process parameter of the corner data. And we made some revisions to make the performance better, including the speed revision. We use the AM with 2 hidden layers, and we also revise the MSE loss. And for the speed revision, here we use a camera to monitor the speed during the printing process. And there are some details for the speed measurement and correction. Yeah. And after we have this DM model, we want to improve the accuracy, so we did a online updating. So we collect, when there are more data inputted, we repeated the second step, and we keep updating the model. So and use the online updated DM model to do the corner height estimation. And here are the experiment results. For the initial model, we use the straight line data to do the experiment and the test. Here are the AM model achieves the best result. And second, we developed the DN model use multi-layer corner deposition. We deposited the L shape, and here are the results. We can see that the DN with speed correction can achieve better results than AN model. And the third one is the online updating model. We have tested 5 batches of data, and you can see there are a slight improvement when we have more data inputted. And here are the final results of the layer height estimation for multi-layer corner data. And you can see estimation with the updated DN is more close to the reference data than the just the AN model. And yeah, and this is the quantitative results. As we can see, the proposed DN model can substantially improve the corner height estimation, and the improvement is more eminent for the smaller corner angle because the printing speed decreased more significantly at corner parts with smaller angle. And the overall RMC value, the overall performance will be 25.7 micrometer. And to summarize, we have achieved the real-time layer height estimation during multi-layer DED process, and we have established AN model based on straight line data, and then use more amount of corner data to develop DN model for corner height estimation. And we tested with different angle, and the overall performance is 25 micrometer. And there are also some limitations, like we only, this work is only for layer height, but we haven't considered the layer width. Yeah, and this is all my presentation.